Hello, everyone, and welcome to the AST and me. So I'm Emily Morehouse. I'm the co-founder and director of engineering at a boutique software shop called Cuddlesoft. Like you mentioned, I'm from Denver, Colorado, by way of Florida, where I lived for most of my life. And I've got my Twitter and GitHub handles here. So what we're going to cover today is a 10,000-foot view of how we get from source code to execution of a piece of Python code, how to interact and inspect each step of that process, what kinds of optimizations are currently implemented in Python in the compilation process, and then some practical applications of how to use ASTs both inside and outside of the Python world. So the question is, should you care about Python internals? And I think, yes, you should. So let's take a quick peek under the hood of Python. So we'll start our journey from source code to execution to try to build an understanding of the broad steps that it takes to compile a piece of Python code. So the first question is Python interpreted or compiled? Yes, and that is the exact right answer. It is both. So our compiler generates a bytecode, and our interpreter makes sense of that bytecode in order to actually execute your code. So one of the ways in which Python is dynamic is that the same bytecode does not necessarily always have the same outcome. So let's zoom in a little bit to see more of what this process actually looks like. So we start with a piece of source code. That source code gets parsed into a parse tree. Now, parse trees are a little bit more detailed than what we actually want to work with. You'll see a diagram of this in a moment. So we transform our parse tree into an abstract syntax tree, or an AST. We then transform the AST again into what's called a CFG, or a control flow graph. And so that's basically a directed graph that models the flow of your program. From there, we finally get to emit our bytecode, and then we can execute our bytecode and get our output. Now, this process is quite intricate, so we're going to focus on a few key parts of this process, namely taking our source code, looking at our AST, and then the bytecode that gets generated from that AST. So what actually is an abstract syntax tree? Essentially, you can think of it as a tree that represents the structure of your source code. But what is a tree? So this is a tree, and this is also a tree. So just so that everybody is on an even playing field with exactly which one of these we're talking about, let's go through a few key components of how a tree is constructed. So trees have one single root. It is the top root node. Nodes can branch off of your root node to other nodes. But each node, except for the root, has a single unique parent. So when we read this tree, we want to start at the top node and work our way down as far as we can on our first branch before we start on the next side. So this is performing a depth-first traversal of our tree. So let's look at the difference between our two types of trees that we've talked about, parse trees and abstract syntax trees. So we're going to take a look at what these trees look like for this very simple piece of code, 1 + 2 × 3. And so on the left here, we have our parse tree for this very simple piece of code. So this is essentially going to be a one-to-one mapping of our source code based on our programming language grammar in tree form. So this is actually a little bit more detailed than we want it to be, as I just mentioned before. So we can actually simplify this parse tree down into something that's a little bit more workable. So here we have an AST for the same exact piece of code, but you can see that you've got a lot less to work with here, so you've got a lot more that you can actually do to transform this tree in an easier fashion. And this allows us to focus on how all of our underlying objects are structured without worrying about our syntactical differences. So for example, for this piece of code, everybody here knows the order of operations. So we know that there is not going to be any need to really pay attention to, say, parentheses that were thrown into this code. So from here, now we have a little bit of an understanding of the life cycle of a piece of Python code. So let's see how we can actually interact with this process ourselves. Enjoy the cute puppy. So a few primary tools that we're going to use are actually a few libraries that are built into the Python language itself. So the first is the AST module. We'll also use the dis module, which is short for disassembler. There are also some very interesting other libraries that I've found useful. One of them is called Aster. There's another one called Meta and CodeGen. Now, some of these don't fully work with Python 3, but they do for the most part. So just remember that we are a very open and accepting community, and we will still treat these libraries as valid, even though they don't fully work with Python 3 yet. So we'll start with a very simple piece of Python code, a print statement that takes in a string as its argument. So we can take this source and generate an AST using ast.parse. So we specify the source as well as the mode that we want to process our code in, and it spits us out a tree that we can interact with. So now that we have this tree that's generated from our code, you can see that it is of type ast.expression. It is very loosely privatized by the ever-known underscore. So what does this tree actually look like? Well, we can dump the AST, but that doesn't necessarily give us anything that's extremely legible right off the bat. We can look closely at this and see that we have a function called print that takes in a string, but that's pretty much all we can determine from this visualization. But we'll push forward. We can now take this AST and compile it into bytecode by calling compile. So now, this is awesome. We have a code object. So this is really interesting. Everybody always says that everything in Python is an object, and now you get to see what these objects actually look like. So we can do a little bit of introspection. We can dig into this code object. Namely, we can look at our raw bytecode. But again, we're humans. I can't read this to you. I don't even know where I would start. But we can now take this compiled code object and execute it simply by calling eval on our code object itself. So let's take a closer look at that bytecode because it wasn't very readable when we saw it the first time. So somewhere along the lines, the compiler is going to take these bytes and make sense of it, but it would take us a long time to find that huge switch statement that actually handles which opcode is being used. So we can use our disassembler in order to print this out in a more human-readable fashion. So now we have something that we can actually understand. But what does this actually look like in an AST form? So here we have the AST and the disassembled bytecode for this print statement side by side. So this is actually pretty readable at this point, especially for such a simple example. We see that there's a single statement, so we don't need any nesting in our AST. We'll call load name on our print function, and then load const for our string that we passed in, and then we simply execute and return. Sounds simple enough, right? But as we add more and more code, even just a simple statement, like an if statement, you can see that your tree is getting just as complex as your bytecode that's disassembled. So our AST still helps us visualize the path that our code takes, much easier than just looking at the dis output that has everything in a single thread. However, something that's very important to note is that what we wind up with in our AST or our bytecode is not necessarily going to match our source code one-to-one. There are certain shortcuts that our compiler takes when it creates bytecode. So let's take a look at what those differences might look like. So Python's compiler is purposefully very simple, or at least as simple as it can be at this point. The best way to optimize Python is to actually switch out your interpreter entirely. So that's why things like PyPy, Jython, Cython, the list goes on, actually exist. Python, the language, can be completely independent of the implementation used to bring the language to life. So one optimization that does exist is the peephole optimizer, which we'll go through. And otherwise, there are very few AST optimizations that occur besides something called constant folding. So let's talk about peephole optimizations. So the way that I like to think about peephole optimizations is looking around without moving your head. This is relying on things that you have in your peripheral vision that you can use to make smart choices about how your code can be optimized. So if you look at this example, this is very simple. This isn't actually one that occurs in Python itself, but I think it's a really good example of how to visualize this. So if you have x equals 1 and y equals x plus 2, we as humans can look at this and go, oh, this is very simple. I'll substitute the 1 in for x, and this quickly becomes y equals 1 plus 2. And so here's an example of a peephole optimization that Python actually does do. So you can think about this as fixing your double negatives. So if we look at our disassembled code for not A, not in B, it's actually the exact same as doing A in B. So the peephole optimizer will actually see that you use two negatives and say, no, we don't need to do all this work. Let's just simplify it down. So the other example is constant folding. So constant folding is the process of recognizing and evaluating constant expressions at compile time rather than computing those things every single time at runtime. So if we look at this piece of code, we can see that the tree is somewhat simple, and the disassembled bytecode has about 4 operations. So in this example, you're not going to really see a huge speed up, but there are going to be a few operations that can be removed from this tree. So if we can evaluate this and just say a equals 6, we can now treat it as a constant instead of having to go through any sort of arithmetic operations. So how does the AST actually affect your code? So now we know that bytecode is created using an AST. We also know that bytecode is stored in PyC or py.o files, which, if you're using Python 3, which you should be, is all neatly organized into your PyCache folders, so they kind of get out of your way. But like we mentioned, you're really not going to get a whole lot of speed-ups from these operations. Everything's going to be extremely micro. So how can you use this newfound knowledge to actually put it into practice? So a few practical applications is to improve and speed up your code if you're really, really concerned about micro benchmarks. You can use this to debug errors. There are a few different interesting situations that the peephole optimizer will actually remove little bits of your code that you might want to test to get 100% coverage. And in some situations, you won't actually be able to do that because the peephole optimizer removes that part out of your code. You can have some fun and get in there and change the Python grammar and learn a little bit more about how this process is actualized in code. One of my most interesting things that I found doing all this research is something called round tripping. So essentially what you can do is you can compare the AST for a piece of code, lint it, and make sure that it is, in accordance with all of your PEP8 rules, and then compare the AST after you've linted your code to ensure that the syntactical differences that you've made don't affect the underlying meaning. You can use code generators. There's actually a lot of code generators in the CPython compiler itself, or you can use code generators to do something like solve a Sudoku puzzle of whatever possible size that you would want to make it. Like I mentioned, there's also alternative interpreters from Python or to Python. So one of my favorite projects that uses a lot of this information is called PyB. So what PyB is going to do is it's going to take your Python code and it's going to transpile it into native Java or iOS code, whether that's Swift or Objective-C. And there's also a variety of tools. So Ginger's another one that if you're doing any sort of web programming, somewhere along the lines, one of your packages is probably dependent on Jinja. And so what Jinja will do is it'll take your HTML code, parse that into an AST, fill in all of your variables, and then pipe it back out in actual HTML that your browser can render. So what are some applications outside of Python? So you can use ASTs to do varieties of code analysis or code linting. There's also tools such as PostCSS or Babel, if you're in the JavaScript world, that will essentially allow you to take CSS or JavaScript, transpile it into something that is more readable by browsers, or that you can actually kind of improve your code or reduce your boilerplate in order to have different mix-ins or functions that you can use to improve your source code. And so this is not for your eyes now. This is for your eyes later if you're interested in looking at any of the resources that I used for this talk. And otherwise, that is it. This talk is also hosted on my GitHub. I was actually very transparent about the process that I used for this. So all of my conference proposals are open sourced, and this repo is completely open and version controlled, so you can kind of see the process that it took me as a first-time conference speaker